We present Diffusion in the dark, a diffusion model for low-light text recognition. Capturing images is a key part of automation for high-level tasks used in autonomous driving, security monitoring, and so much more. Low-light conditions pose a unique challenge for these tasks, as these perceptual stacks are often trained using only well-lit images. Existing low-light reconstruction methods typically use CNNs to predict well-lit images through direct regression or GANs to predict the realism of the reconstructed images. However, we are not only interested in reconstructing aesthetic images, as these methods often opt for, but also images with high-frequency details to perform high-level tasks, such as scene text recognition. Reconstruction of high-frequency details remains a difficult challenge. It's long understood that CNN-based methods tend to estimate a blurry average of possible reconstructions, while generative models such as GANs can better hallucinate fine details. However, it's well known that training GANs is a hard task, which can be unstable and lead to mode collapse. Fortunately, diffusion models have emerged as a powerful alternative in generative models, and these perform just as well as GANs with better properties. In diffusion models, training involves a forward process in which training images are noised to assume white Gaussian noise, and the same number of steps can then be taken in the backward process in which the noise is iteratively removed to recover our image. We train the model to learn the distribution of well-lit data while allowing us to recover plausible high-frequency detail. We present Diffusion in the dark, a diffusion model designed to reconstruct high-frequency details for low-light text recognition. These are results based on our reconstructions and text predictions using a state-of-the-art scene text recognition method. We first introduce a couple of conditions that we'll use in our training. We use low-lit and well-lit pairs to train our diffusion models primarily, and we simulate a well-lit but low-resolution prediction, which will serve as an estimate within our multi-scale approach, and we generate this by downsampling and upsampling the image. We also simulate a first estimate condition, which is also the well-lit image, but at the lowest resolution, and this simulates an estimate from our first scale of our multi-scale approach. We also note that training a diffusion model on large resolutions is incredibly computationally demanding. Thus, we opt for a multi-scale patch-wise approach, which in theory allows for reconstruction at any resolution. We take these three conditions, we break them into patches, and use them as conditioning estimates to denoise a noisy signal to our clean, well-lit image. We then compute a loss against the same patch from our ground truth well-lit image, and during every training iteration, we select a random scale to size the image and take 32 by 32 patches from. During inference, we downsample our low-light image to be 32 by 32 and make 2 extra copies to simulate the other conditions that we just mentioned. We pass this image through the network to predict the first estimate condition at scale 0. We then operate at scale 1, in which we have our low-light input, the well-lit but low-resolution condition, and the first estimate condition. In this case, the last two ones are from our previous scale 0 estimate. We upsample these conditions before we break the image into 32 by 32 patches and pass them through the network. We then stitch them together to reconstruct our scale 1 estimate. We then repeat this process at one scale larger, changing the well-lit but low-resolution condition from the previous scale. And then one more time until we stitch the full 512 by 512 image. Low-light data is inherently right-tailed and remains right-tailed even when z-scored. To train diffusion models on low-light data, we introduce right-tail normalization to have the data assume a normal Gaussian distribution, making it suitable with all the assumptions made in diffusion models. We now show our results. We use a state-of-the-art scene text recognition method, parseq, on reconstructed images and demonstrate that diffusion in the dark reconstructs enough high-frequency details for successful text recognition from dim, noisy conditions. We also test word % accuracy and 1- normalized edit distance both quantitative measures of text recognition accuracy across a number of simulated noise and brightness conditions on text datasets. We compare against vanilla latent diffusion models, LL-Flow, which is the best performing low-light reconstruction method, and our method. Diffusion in the dark far surpasses any other method in text accuracy in simulated low-light text images. We also demonstrate successful reconstruction on real low-light images in the wild. And we show that our method is able to provide reasonably good reconstructions overall, capturing high-frequency details from the signal in the LOL dataset. We also test on other real low-light data and show that our reconstructions often provide more reasonable coloring than other low-light reconstruction methods. Thanks for listening. Stop by our poster.